Hi, my name's Loren. I'm the technical trainer with Genesis Attachments. Today I wanted to take a few minutes to walk through the DCS process with you. For those of you that don't know, the DCS is an acronym for Dimensional Confirmation Sheet. It's a document that we provide to our dealers and our customers to provide excavator and bracket dimensions to guarantee that we build the correct bracket for the excavator that the tool is intended to be put on. There's a couple different reasons why we do it, but most of it is to protect our customer as well as ourselves from having to do extensive rework, prevents delays in getting things operational, as well as having to ship tools back and forth for reworking of things that we should have done properly up front. When we provide a dimensional confirmation sheet to our dealer or our customer, normally we have some auto-populated information in there, the serial number of the tool, the intended carrier for the bracket, and perhaps some dimensions or some pin sizes that we just simply want verification on. When it comes to who performs the DCS, normally that falls on one of two parties. It's either the end user or the dealer. So there can be a few different people that might be responsible or have their hands in the mix. It doesn't matter if it's second member, third member, high reach, scrap shears, demolition tools. We require the DCS for all of them. Most of it can be done without disassembly and with relatively simple tools.
Here's a few of my measuring devices here, and this is just a simple Empire 16-foot tape, and this would be great for pulling some of the longer dimensions, maybe even across the rod eye clevis. But when it comes to measuring pins, it's going to be just about worthless. It's going to be difficult to really nail down some of these pin sizes to the decimal, and a lot of them are going to have chamfered edges on them too, which is going to make it even more difficult to get an accurate number. Not only do you have to make sure that you can hook the pin at the proper spot, you have to make sure you're straight across, and then you're going to have to eyeball this edge, which is below the chamfer. In some cases, if you're measuring bores, you can use something like an inside micrometer or like this, a snap gauge, which you can actually push through the clevis or the rod eye or the bore that you're trying to measure to assist, especially if you're not going to utilize the pin. You can just measure the bore itself. Using something like a square, obviously it's got measurements on here, and you might have some success being able to lay this out and get it relatively accurate, maybe fairly square. Even the use of two squares might be useful, or a straight edge, but this wouldn't be our go-to tool here either. What we're really looking at for pin dimensions or bore dimensions, depending on how you utilize this, this would be the kind of measuring tool that you might have to have. If you have outside micrometers, they work well too, but almost everybody has one of these laying around their shop. This one is fairly long. It goes all the way up to 12 inches, so you can measure a pretty wide span. And then the way you measure the pin too. What I meant by measuring with the tips is anytime you're going to try to measure a bore or a pin dimension, you need to make sure that it's centered. It's a lot easier to get that dimension accurately if you go like this, if you go across the pin. Now, when the pins are installed, sometimes it doesn't allow you to do this easily, but you get a much more accurate number if you can measure this way versus this way. It isn't that you can't accurately measure this way, it's just that it's going to open the door for making an easy mistake for something that could be just far enough off to throw your numbers out of whack, in which case we would either re-engineer or figure a new pin size. So the way you measure these is just as important as which components you're measuring and which type of device you're using.
Let's get into the PDF. Afterward, we'll talk about what we learned.
Okay, so here's a DCS, and what this is showing you here is a portion of the excavator boom and a portion of the dipper stick, as well as a cutaway view of section AA. So what this is doing is it's looking downward at the boom tip. So you see the stick cylinder here, and the pin connection. There's actually two pin connections right there, and on the other view it's going to be right here looking like this. So what I'm going to show you here is the different things that may be on this form, and as well as the dimensions and where to put them when you measure them. And we don't necessarily need every dimension in both inches and metric numbers, but you do have to have one or the other. In a lot of cases it will actually be provided, and all you need to do then is verify it. I'm going to go to a different PDF, but what this is it's pre-filled with some information here. You can see I've got the serial number already there with a generic Genesis customer, as well as an attachment type. Now, some of this information you may not have available to you when you're filling out these forms. The serial number is probably going to be available to you because we have a serial number applied by the time we're putting excavators underneath these sales orders and production sheets for building them. And then there's also going to need to verify the attachment type. You wouldn't need to pay much attention to this rotation swivel reverse. That's something that we use for our own internal use, so you wouldn't need to be too mindful of that. But there may be notes here as well. So if there's, say, some specifications about the bracket type or the arrangement or conversion components or something like that, you'd want to make sure that the notes are accurate, at least to your knowledge. So that would be something to go through before you even start the measuring process.
All right, we're going to start right here on column A, and A is going to be identified on our sheet right here. This circle and the slash through it is going to tell us that we're looking for a pin diameter, and you can tell that the arrow is, this little slight gray arrow is pointing towards this component right here. So what we want to do is we want to measure this pin for diameter. So these are difficult to get with a tape measure. You'll probably have to use a micrometer or something where you can actually make an accurate, high precision measurement. The graduation on a lot of tape measures isn't fine enough to get a good dimension confirmation from a simple tape. So what you'd want to do is measure across it, make sure you're doing it in the proper way. If you utilize the tips and you measure off the end of the pin, sometimes it can throw your numbers off a little bit. You aren't necessarily measuring straight across the diameter of the pin. So you do have to be mindful of how you measure it and the device that you're using to do it. But once you've determined that you've got a good measurement on that pin, you can come down here and look at, either 4.33 inches or 110 millimeters, and either check it off, verify it, initial it, whatever you want to do, or fill in corrected information. So if this were a 100 millimeter or a 120 millimeter pin, you could fill that in, and then we could document it as such, or perhaps verify with the OEM manufacturer about the pin dimension or the change that may have occurred with a particular serial number or prefix code. And then we can move on to item B.
Item A, measured with the caliper. Pin dimension here. On this one, the pin is not protruding far enough to get a good measurement on it. So you need to remove the retainer, bump the pin out, measure it from the other side.
Item B is in this column right here. This particular unit is showing that that dimension should be 319.53 millimeters wide. I'm going to zoom in a touch here so you can see this a bit better. But what we're going to be measuring here is the boom tip width. So it's the inside dimensions. So what we're looking for is a face-to-face measurement. So our lines there are pointing to these two faces. And what we want you to do is draw a tape across the two surfaces to confirm this dimension. Now you can see my arrow here is a little crooked, so you'd want to make sure that you pull straight across. But it should be a relatively easy measurement to capture, and here's one where you could do it with a properly graduated tape measure. You can certainly pull this with a metric tape or a standard one. You just need to make sure that you're putting the correct information in the correct line. So when you come back down here, you'd either want to verify this 12.58 or this 319.53 millimeters, depending on what your measuring tool is.
Item B, inside boom tip width. This is easier if the stick isn't in your way. You may be able to sneak a caliper through here. If you don't have a caliper big enough, in some cases with larger excavators, you may just want to push a tape measure through here. Capture your measurement this way. Keep in mind, you use the tape correctly so that you have a good end on it, and you're butting it up tight to the inside of the boom ear.
Continuing with component C, 119.38 millimeters, we're actually going to be looking for a rod eye width. So back up here on this top graphic again, I'll zoom back in. We're going to be looking at this dimension from this arrow to this arrow, and what that is it's the rod clevis up on the top of the boom. So it's actually this cylinder right here, but we're not interested in the stroke length or the pin diameter. What we really want is the clevis width. So what we want is right here. So we need the surface that this total clevis width from side to side. So depending on how yours is built and how it's arranged, it might require bumping the pin out so you can get at it properly, but it shouldn't be too terribly difficult to get at. And once you've got that dimension, you'll come back down to your number C and verify the dimension down here, initial it, check it off, correct it, whatever it may be. And if you see a number that's off by a little bit, you certainly want to double check it, even triple check it. And in some cases, it may be necessary for you to actually pull the pin out, lift the cylinder up a little bit, get it at a point where you can truly access it properly, and you might have to pull a better dimension off of it.
Item C, rod eye width. You'll want to clean the grease off of here. Pull your caliper across here, make sure you have good contact between the tips. Record that dimension, put it on your sheet.
So here's component D. I already zoomed in a little bit, but what you can see here is we're going to be looking for another pin diameter. So this little circle with the slash through the center of it tells you that we're looking for a diameter, and that guy is going to be right here. So if the pin is not exposed on either end, you may have to remove the bolt or the pin keeper depending on the design, and you may need to bump it out perhaps with your hammer handle. If there's not a lot of tension on it, shouldn't be too hard to move. Take your dial caliper or digital micrometer, pull it across the sides of the pin, confirm that dimension, and then come back down here and verify the pin size.
Item D, measure the pin across this diameter. This is also a tough spot to get. It looks like I actually could get a good measurement off it, but I'd rather remove the retainer, bump it out a little bit, and measure from the other side.
Item E. You won't be able to do this with a micrometer or a digital caliper unless you've got one that's several feet long. But what we're looking for here is this component, and what this is it's actually a pin center to center. Here's where you got to be careful. You cannot pull pin edge to pin edge because you may have two different size pins and it will throw your numbers off by a little bit. So this is the dimension that matters, where it's going to determine how far the shear tucks underneath the boom, how far it reaches out. And one of the things that we need to be careful of here too is if we get this wrong, when this cylinder extends and retracts with normal motion of the shear reaching or tucking, if it's wrong, it can actually get to the point where it'll start to actually rotate around the center pin, and if it goes too far, the cylinder can actually toggle over the top of the connection. So if the dimension is too short, you'll end up with this extended range, which is great, but it'll actually come into the possibility of interference. So you may have a contact point here. Now, if the pin centers are too long, you'll actually end up with a shear that won't have the correct geometry, so it won't have the intended range of motion that it should. So it'll be stuck swinging in, say, a 90-degree arc instead of a 120-degree arc, where the shear will reach out well and tuck under well. So you want to be mindful of that, make sure it's correct. And if you don't have the boom, or the stick available to measure, we may have to use other means to reference this number and get the information from the OEM manufacturer.
The final dimension is D. These pins are actually marked with their centers. Pull with a tape measure across here, capture your dimension, transfer it to your sheet. Bigger excavators, the distance is going to be further apart. Smaller excavators, typically closer together.
Not every DCS is the same. There are lots of different versions of them. We make a lot of different brackets. We don't necessarily provide a different DCS for each type of bracket, but there are some other ones such as couplers. So when it comes to these coupler components, it's the same process as what we had just done with the other bracket type. So obviously there's some differences in the way that A and B and C, D, E are laid out. But if you find the component up here on the PDF, it shouldn't be too hard to discern exactly what dimension we're looking for. Some of these might be a bit more difficult than other. You see this one up here, it looks like it's letter E, which is at kind of an odd angle, but essentially what we want here is this pin grabber dimension. We're no longer concerned about the excavator dimensions when it comes to putting a shear or work tool on it. We're actually worried about the coupler dimensions. So that whole aspect of trying to measure the excavator kind of goes out the window. Once we know the coupler, the pin sizes, the dimensions, the grabber type, those sorts of things, we can build the bracket to fit it.
One more thing that you need to consider when talking about pin grabbers is the pin type. So when we direct pin a shear or a demolition tool for an excavator, if it's direct pin, what we normally would use is an induction hardened chrome pin. So
The induction hardened chrome pins are great because they're extremely strong in shear resistance. So if you have multiple bores where you're passing a single pin through it and the pin faces or the bracket faces are adjacent to one another, the IHC pin is ideal because it has incredible shear strength and it also has very good wear characteristics. But with a pin grabber or a coupler, we're looking for different properties. So rather than having an IHC pin where shear strength is its greatest benefit, what we want there is an annealed pin. The annealed pin is softer, not necessarily prone to wear, but doesn't necessarily play nice with bushings and other components that would be slid together through a bore that like we would utilize with the IHC pin. So the annealed pin has other benefits though. It's a bit softer and it can actually flex. So when you grab an annealed pin in the center with a grabber or some type of coupler, the pin is going to be far less likely to fail. So it can flex and return or resist breaking. So it may not have the ideal properties for the direct pin coupling, but it's perfect for the coupler or the grabber situation where the pin is going to receive a lot of abuse in the center or throughout the entire length of the pin rather than just in shear. So one situation that you'd have to look out for is if you are converting a direct pin work tool to a coupler. So even though the bracket may physically work because the geometry is correct, if the pins are wrong, you do run the risk of breaking the pins, and in a severe situation, you could actually break the tool free of the carrier. So you do need to make sure that you're sourcing the right pins for your application.
Well, there you have it. Hopefully by now you understand what the DCS is, why we perform it, who does it, and the reasons for it. If you have any questions on this process, please feel free to contact our outside sales group, inside sales group, or the Genesis Service Department. We can be reached at 1-888-SHEAR-IT. Thank you.